So I hope you are able to see my screen. So we'll start today's session. So before going to start the session, I will introduce myself. So welcome all of you. I'm Vijay Rane and I'm a Prime Minister Research Fellow in the IIT Delhi. So today we are here to discuss some of the problems based on the week 9 content of the course molecular rearrangement and the reactive intermediates in the organic synthesis. So before moving to discuss. So I would ask to you if you have any doubt, please let me know that we can discuss first, and then we'll move towards the problems. So does anyone have any doubt regarding the particularly the week 9 topics? So basically, week 9 we have covered like reduction of carbonyl compounds. So that we have covered in the week 9. So regarding this, do you guys have any doubt? So if you don't have any doubt, I will slowly move to the some of the problems and the uh, it will be today's session will be cover some of the reducing agents. So particularly, I have taken some of the examples so that we uh, these are the some problems that we have already solved. So So the first question that I think this question we have got again last time also. So based on the reduction of such compounds, so in this one, as we have seen, uh, due to the steric crowd of these hydrogens, so the hydride attack at the from the bottom side is will be difficult, and therefore the LiLH4, so the hydride minus attacks on the top side, and we get the hydrogen attached here and hydroxy group directing downward. So we get the product B as a major products, and we have also seen the detailed mechanism. So uh, this is what the intermediate step that makes the steric crowd, and that's the reason we get the uh, endo-directing alcohol as a major product. Then we have also seen the some reduction in the BH3THF. So that's again the mechanism of this which has the boron deuterium bond is add syn side to the double bond, and further the H2O2 attack on the boron, and followed by the syn hydroxide transfer to the carbon from the boron, and it gives the product which has the new attack groups are on the syn side. And similar case with the when we have the hydrogen, instead of BD3, here is the BH3. So that's the difference here. So these problems we have already discussed in the last week. So today particularly I like to take revise some of the reducing agents. So these problem also that covered in the last week video. So you can refer the last week video. So that I will not discuss today again. So basically, today I'm planning to cover the reduction of the carbonyl compounds. So we'll revise some of the reducing agents. So we have in the carbonyl compound, we have the acyl halides like acyl chlorides, bromide, or the such acyl halide compound. Then we have the aldehydes. So which has the in the carbonyl compound we have the aldehydes which has the carbonyl and chloride, carbonyl and hydrogen bond. Then we have the acid. Also the there are again nitriles or the uh, imines, also amides. this sort of the compound which is involved the carbon heteroatom double bond, and the reduction of such double bonds are different reagents are particularly used for getting selectivity, and also for the in some cases sterically control reduction can also be takes place. So that will revised in this today's discussion. So if we have such compounds, and particularly, so we'll devise concept of the chemoselectivity here. So if you have such compound which has the carbonyl group, that's the keto, and here there is another group, that's the ester. So here there is a keto group in the same compound, and another group is the ester group. And if we want to selectively reduce the keto group, so at that time we need to use the chemoselective some reagent so that selectively reduce the keto and without affecting the ester group. So you can see here, so the ester group is retained in the product, and so we get the final product as a alcohol from this compound. So which reagent which should use to convert this conversion? So that comes in the category of chemoselective reduction. Then if you have the regioselectivity, so let's say here uh, we have already seen some example with the in terms of the such reactions. So we have the one functional one compound which has the carbonyl group, and another group is the alpha beta unsaturated double bond. So we need to do the perform uh, such a reduction to get only reduction of the double bond without affecting the carbonyl group. So in that case, we need to do regioselective reduction of this double bond. So this type of reaction we call it as a regioselective reactions. So in this, reagents add only at the only one of these possible region and unaffecting the other one. So this one is the unaffected. So uh, this is the example of regioselective reaction. And again, there is again example of the stereoselective reduction. So let's consider this simple example. So which has the compound which has third butyl group and the keto group, and we need to if you do the reduction of this compound, and uh, let's say we get such product in which the hydroxy group and the third butyl group is anti to each other. So when you get such a reaction and this product get as a major product or in the form of inertial excess, that time we call this type of reduction as a stereoselective reduction. So this stereoselective reduction leads to exclusive or predominant formation of one of the several possible stereoisomer. So when the stereoisomers are the product, that time we called it as a stereoselective reduction reaction. And again, we have the stereospecific as well. So let's take this example, which has the, so this is the example, and as you can see here, so in this example, I'll just remove all the remaining some earlier drawn, right. So in this example, as you can see, we have a trans alkene, right? So in this trans alkene, upon bromination, so this bromine adds to anti to each other. So this sort of and we get only the mesoisomers. That's the so mesoisomers. What is the mesoisomer? So if we just draw in that form of 2D, so that's the Br, and here is the hydrogen, the CH3 and the CH3. we call this isomer as a mesoisomer. And if you have such like hydrogen, the bromine here, bromine here, and hydrogen. In this case, this is one of the enantiomer. This is not a mesoisomer. So mesoisomers have the plane of symmetry. So such reactions give the substrate given substrate isomer leads to the one product, while another stereoisomer leads to formation of opposite stereoisomer product. So let's uh, let's say here we have the trans, but at some point when you perform such reaction on the cis, then we get some different a different product. So these are some stereo-specific reactions. We are going to see that when we study example of such reduction losing agents. So at that time we are going to see, and here the reduction in some cases, if we have the prochiral center, so this carbonyl center is generally prochiral center because upon addition of these any nucleophile across the carbonyl center, that time we can convert the center into the chiral center. So it is always considered as a prochiral center, and so there is chances of stereoselective product formation in this. So I will give one example. Uh, so the reaction across this carbon group also involved some stereochemistry aspects, because let's say in this one, if you do the reduction, we will get only one type of OH, whether it is directing downward or upward, both are equivalent, right? So hydride, let's say you do the reduction. If hydride attack takes place from the bottom side, then we get the beta directing alcohol, and if hydride attack takes place from the front side or from the top side, we get the alpha directing alcohol. But in this case, both are equivalent, because there is no any, what you can say, both the side chains or the this carbon has the plane of symmetry, this starting material. But if you have the some substituent which has the, let's say here it is a methyl group is directing, which is down, which is beta directing. At that case, the product we are getting by uh, attack by the these two manners. Let's say we consider attack by the attack from the bottom side. At that time, we get the beta directing alcohol, and here the methyl is again methyl. The stereochemistry of this side group will be remain same. And another possibility is the attack from the top side. At that time, we get the hydroxy group directing downward, and this methyl group will be remain same, the stereochemistry of this methyl group. So at that time, these two are not equivalent. These are basically the enantiomers of each other. So uh, here we get the two different product. Now depends upon the reagent we use, or also the stereochemistry of these center of this chiral center. We decide the stereochemistry. So this type of reduction also we will see here. So dominantly. So in this case, let's say we do the reduction with the normal NaBH4, and we have such starting. So let's say take one of the example. So we have such starting, and here we have the directing group, which is directing beta. So this is also one of the group which is directing beta. So at the time, if you do the reduction with the NABH4, at the time the hydride attack is takes place from the hydride attacks. So this is the hydride, and this hydride attacks is only possible from the bottom side or opposite to the this bulkier terbutyl group. Why? Because attack from this top side is sterically hindered because of this bulkier terbutyl group, and we get here in this case the product selectively. So this group remains same. So this terbutyl group remains same, and hydroxy group will be now will be on the seen side. Why? Because the incoming hydride attacks was on the bottom side. So this is what product we get as a major product. So this type of reaction we call it as a stereoselective reduction reactions. So here are some examples of the reducing reagents. So mm, generally there are certain categories of such reducing reagents. So here NaBH4, LiLH4, they are considered as a nucleophilic reducing agent. And here, if we look at the what are the examples? So here, either NaBH4 or lithium aluminum hydride. So you can see here AlBH4 or NaBH4 here also. And in this case, the reducing the hydride is the source of electron that attacks on the carbonyl group, and the metal centers, as you see in general formula, either EMALH4 or FBH4. In that case, this EM can be the either lithium or sodium or the zinc. So we have seen some examples of the reduction reactions with the zinc borohydride, also with the lithium aluminum hydride or sodium borohydrides, this sort of reducing agent. And if you look at the reactivity order of this reagent towards the carbonyl compounds, so aldehydes are highly reactive compared to the ketone, and which is then compared to the ester and compared to the amides and the acids. So this is what reactivity order for such reagents. So in this case, you can list what are the examples. So AlH4 for LiLH4 or for NaBH4 or for ZnBH4, the same reactivity order will be followed. So aldehydes, then keto, then ester, then amides, and then the acids. So you can keep remembering this reactivity order of this. Then we have uh, I believe the mechanism I don't require to really explain for how the reaction works with the LILH, each reducing agent. So here just the here just the mechanism that shown for the reduction with the LiLH4, that's the lithium aluminum hydride. So this is reagent is the most powerful reducing agent, and generally this is not as mentioned here. You can see here not give any chemoselectivity reduction. If you have some molecule which has the aldehyde or keto group, ester group in the same molecule, so all groups will be get reduced by using this LiLH4, and you can see the reaction mechanism. The hydride transfer takes place to the carbonyl group, and OLI bond is getting formed. So as a intermediate. So this is what reaction mechanism with the LiLH4, and same reaction mechanism is with the sodium borohydride also. So you can refer the detailed reaction mechanism from this slide. So this involved in case of the ester, always remember first reduction gives the keto group, as you can see here. Once this intermediate form, this OR group is get eliminated. So minus LiOR, it gives the sorry, the aldehyde. After upon reduction of the ester, it first gives the aldehyde as a product, and then again reduction of the aldehyde takes place. It gives the alcohol. So two times two equivalent of the LiLH4 required to convert ester to aldehyde. And if you look at the uh, how much equivalent of hydrides are getting converted, particularly for each of the substrate. So if you have the aldehyde, so one equivalent of hydrides are consumed, it gives the formation of the alcohol. Then we have the keto group. Then in terms of keto also, it will give the alcohol. Then we have the, let's say, the acid. So it use the three equivalents of the uh, lithium aluminum hydride. If you can say why three equivalent, because if you look at the acid, so we have the in the acid. So this is the general structure of the acid, right? So the first hydride will be utilized in the abstraction of the proton. So it gives the H2. So the first byproduct formation is the H2 gas. Then we get from this acid to the O negative. Then the second equivalent of the hydride is used for the converting this alcohol to this type of uh, this sort of intermediate, and the third equivalent. So upon this one, it will again eliminate this entire species. So it gives the like this aldehyde intermediate, and then third equivalent will be used for the reduction of this aldehyde. So total, the first equivalent, the here the second equivalent, and here third equivalent. So total three equivalent of H2, sorry, the hydrides are consumed in case of the acids, but that's not the case with the ester. So only two equivalent. In case of amide, again two equivalent. The product with the alcohols as well as the esters, they are obviously the alcohol, primary alcohol generally. And with the amides, we get the primary amines as a product. Then if you have the cyanides or C triple bond N, then in that case also we get a primary amine as a product. Then if you have the lactones or the peptides, so lactones give the diol formations, and epoxides give the alcohol formation, depends upon the and it consumes the lactam consume the two equivalent of the hydrides. Also epoxide consume one equivalent. But if you have the isolated alpha, sorry, alpha isolated alkene. So LiLH4 doesn't react with the unsaturated, sorry, the carbon-carbon bond, isolated carbon-carbon double bond. So if we look at the this is the one of the reaction, and if you want to see this example, so if you have the ester, alpha beta unsaturated ester, in that case, when you react with the one equivalent of the LiLH4 and the triethylamine equivalent in THF solvent, we get selectively ester converted into the aldehyde. So without further reaction, and this reaction gives the 93% of yield. So here, this reaction is controlled by the equivalence of the lithium aluminum hydride. So for that, the earlier chart that we need to, it will be helpful. So if you add selectively lower equivalent, that case we can able to control somewhat uh, reaction. So in this case, if we add the excess of LiLH4, we can directly get the alcohol. But in this case, we have added the one equivalent of LiLH4. So therefore, we get alpha beta unsaturated aldehyde as a product, and which is, if you look at the yield, which is quite excellent, 93% yield. Then we have the another reagent, that's the lithium trialkoxy hydride. So in that case, this is again kind of reducing agent. Only thing, this reagent is slightly less reactive compared to the earlier LiLH4 reagent. And in this case, instead of the four hydrides, the three hydrides are substituted by the third butoxide group, and one is the only hydride left out at the aluminum center. So this will be the tri. So if you look at the structure, so this structure itself indicate, so it is quite bulkier reagent, and also only one hydride is available with the Al. So it will be a mild and less reactive reagent. So if we have such, let's say, acyl chlorides, and which has the C triple bond N, and if you want to selectively reduce only acyl chloride to the aldehyde, at that time we can use such reagent. So you can see uh, how you can modify the reagent. So this is just modified LiLH4, and which helps to selectively perform the reduction of acyl chloride to the aldehyde. Then we have the lithium triethoxy. So earlier we have seen the tri terbuto. So this we have seen this reagent, right? Now here we have the triethoxy. So instead of this terbutyl group, here there is only ethoxy subunit. So this will be slightly stronger compared to the earlier one, because because of the steric bulkiness, this hydride is very weakly reactive. But if you have the such group, so this is slightly strong reducing agent. And if you have such, like let's say the amides, so this amide can be converted into the aldehyde by using this reagent. Also, if you have the cyanides, or let's say C triple bond N. So in that case, only one hydride attack with this reagent takes place. So it will first lead to the formation of R C double bond N, and here H, and upon hydrolysis, this imine can convert into the aldehydes, right? So that's reaction. I believe you are aware about this reaction. So we get the aldehyde as a product from the cyanide also. So this is the beauty of modifying the reagent. If you use the directly lithium aluminum hydride, but at that time we directly get the alcohol, not the directly get the from this one directly the CH2 NH2 that's the product we will get from the LAH. But with this reagent, we can get the aldehyde as a product. The next reagent is the sodium borohydride. And if you look at the sodium borohydride, this is similar to the mechanism of this reduction is similar as the lithium aluminum hydride. So this hydride source attacks on the carbonyl. It gives the formation of alcohol, and there is no further reduction takes place with this reagent, right? So alcohol we get as a product, and in case we have the in the reaction keto group ester, and here we can see alkyl halide. In this case, if you use the sodium borohydride, we can selectively reduce only the keto without affecting the alkyl halide as well as esters. So this will give only reduction of the keto. So this is milder reducing agent. Here you can see the some of the some examples. So let's say we have in the product we have the acid. Further, in this case, we have the NHC double bond O H. So that's the aldehyde attached to the nitrogen. So in this case, if you add the sodium borohydride, it gives the formation of alkyl aldehyde convert into directly to the CH3 group. So this is the reaction condition. The sodium borohydride followed by the I2, then the methanol workup. So this is what product get with this reagent combination. Then we have the similar to the sodium borohydride, we have the lithium borohydride. So this lithium borohydride works. This can be prepared from the sodium borohydride. So here we need to add the LiBr salt in the sodium borohydride. So when you add the LiBr salt in the sodium borohydride in the dry ether, so that case we can convert into the LiBH4. Here we have the as like sodium borohydride, aluminum borohydride, zinc borohydride can also be prepared. So this zinc borohydride is the it can be prepared from the zinc chloride, and the starting material for preparing this reagent is the sodium borohydride plus zinc dichloride. So it gives the ZnBH4 twice, and this Zn borohydride can be uh, so this reduce the aliphatic ester and the carboxylic acid, and also effectively hydroborating agent for the alkenes as well. So if you have the alkenes, as you can see here, so these alkenes can also convert into the alcohol by using this Zn borohydride. And if you have the acid, so this acid can directly convert into the alcohol by using this zinc borohydride. So if you use the NaBH4, this reaction will not work. No reaction with this with the acid. But if you use the zinc borohydride. So it will convert acid to the alcohol. Then let's take some example. So let's say if you have the such group which has the tosyl alcohol protected with the tosyl group, and if you add the Li lithium triethyl borohydride, in that case we get the entire group will be substituted this hydride directly show the SN to substitution, and this entire OTS group is eliminated. But if you use the LiBH4 in ethanol, in that case, this OTS only the it conjugate we get the product as a alcohol. Here again, some of the examples of the stereoselective reduction. So if you look at the this compound which has the keto group, and we use the sodium NaBH3CN sodium cyanoborohydride. So in that case, the stereochemistry, if you look at the stereochemistry, this ester group directing downward. So you can see this ester group directing downward. And however, this methyl is also directing downward. It indicates this by this bridged two rings are in the concave fashion because these groups are directing downward. So obviously, uh, this group must be the upward, and this group also must be the upward, right? So, and in the plane there will be lone pair. So this is what the structure will be looks like with from this molecule. And if you look at the concave phase, so the approach from the concave phase will be difficult, and therefore the on the convex phase the sodium cyanoborohydride attacks, and we get the alcohol directing upward, as you can see, and this hydride, that's the attached newly, will be directing downward here. So if you look at the structure, uh, someone may directly end up to the conclusion that the adjacent group is directing downward. So from attack from the downside will be the sterically hindered, but that's not the case with this one. If we have some plain molecule, in that case it is okay, but not in this one. So if you have such molecules, so C double bond O E T, and if you have such molecules, if you have such molecule, in that case, this if you have attack the this sodium cyanoborohydride, so this hydride transfer takes place from the top side, and we get the product which has the hydroxy group directing downward. Uh, Again, this carbon C double bond OET group will be again downward, and the incoming hydride will be on the upward. So that's what product we get in this case. But here, because of this concave faces of these two five-member rings, attacks from the concave side will be difficult. Then we have the another reagent, that's the sodium cyanoborohydride. That's already I think we discussed, but some utility of this reagent that we haven't discussed yet. So let's say we have the functional group. So this reagent, if you use the amine, so this amine on the keto group, it can convert into the imine, and this reagent is used for the reduction of the imine to amine. So this will effectively used for the reduction of the imines. Let's say here also. So this NH2 NHTS. So this NH2 in place of alcohol it form the imine, and then sodium cyanoborohydride. If you add that sodium cyanoborohydride, it will convert this imine to the. So in this case, this is the tosyl hydrazine is there. So in that case, it is give the methyl. So that's some of the exception with this one. Otherwise, generally it gives the when we have the imine and we use the sodium cyanoborohydride, so we get the uh, amine as a product. Here again we have the some other reagent uh, like the boron THF, particularly the BH3 THF or BH3 um, DMS. So in this case, they are generally used for the reduction of the acids. So BH3 THF, when react with the acid, it forms such intermediate. So three equivalent of acid attacks with the forms complex with the boron, and then this boron, that's the BH3, uh, attacks on the carbonyl group to convert it into the. So this will be if I just draw the full structure of this one. This is the CH2 and this the R, let's say. So this sort of intermediate. And again, third, again, upon workup of this hydroxy, sorry, the water molecule attacks on the boron, and we get the alcohol as a product. So this bond is getting cleaved at the last stage upon workup. So the similar mechanism with the BH3THF or at the BH3DMS is followed. So you can see here example. So it selectively reduce the acids and without affecting the ester group. So this is the one of the example as you can see here. And if you look at the selectivity of this BH3THF, so this BH3THF, it react with the acid very fast and get converted into the alcohol as a product. And if you add that BH3THF with the double bond, that's the alkene, it will be gives the organoborane as a intermediate. Similar case with the carbon triple bond carbon. When you have the aldehyde, at that time BH3 THF convert aldehyde to the alcohol. Same case with the keto to the secondary alcohol. R suitable one to the amines, the epoxide to the alcohol, and ester into the alcohol. Acyl chlorides doesn't react with the BH3THF. Then the nitro group are nitro or aromatic nitro group doesn't react with this BH3THF. And then we have the acid or the acid salt in the form of salt. That time it doesn't convert, it doesn't show the reaction. So that's what always you need to remember the reactivity of this BH3. Uh, Again, one category of the compound we generally have, that's the alpha beta unsaturated ketones or aldehydes. So reduction of such compounds is much important in our day-to-day life of the organic chemist. So in this case, there are some reagent combination, special reagent combination are needs to use. So that reagent combination, particularly reducing reagent combination, we are going to see in this slide. So if we have the alpha beta unsaturated, whether it is aldehyde or the ketone, the same case with the both. And in this case, by 1,2 addition, we get the carbonyl reduction and keeping the double bond intact in the product. And by 1,4 fashion addition, if takes place, we get the double bond reduction and keeping carbonyl group intact. So sometime we required reduction of the double bond, or sometime we want to keep that double bond. Only reduction of the carbonyl is, let's say, our desired product. So that case we need to choose the reagent combination. So here one of the reagent combination is the cerium trichloride salt with the NaBH4 and the methanol. And when you use this reagent combination, so in that case, we can selectively reduce the carbonyl group by keeping the alpha beta unsaturated double bond intact. So once you use this cerium trichloride salt, this reduction will work in this fashion. But in the case when you use the NaBH4 without cerium trichloride, so that time the double bond will be remain same. Sorry, the uh, it will be show the reduction of this double bond as well. So we need to use the, so better I will draw with the different color. So in that case, we get the, so this is what product we get with when it react with the NaBH4 or LiLH4. So both 1,2 and 1,4 addition takes place. So with this, on this substrate, when you use the NaBH4 or may also AlH4 or any other Li or the other reagent. So this addition of the cerium trichloride is important. So when you want to selectively reduce the carbonyl compound and by keeping intact alpha beta unsaturated double bond. So here I have just listed some of the reagent combination and I will better show it, uh, increase the size of the screen. Right. So let's say we have the alpha beta unsaturated carbonyl compound, and so these are the some possible reagent, possible products. So in this case, only carbonyl group is only carbonyl group is reduced. So you can see here. So this group will be remain in the product. In this case, only double bond is reduced, and in this case, both uh, carbonyl group is reduced as well as the double bond is reduced. So we'll see one by one reagent, right? So when you use the LiLH4 at 0 degrees Celsius in the THF solvent, we get the reduction of both double bond as well as the carbonyl compound as a major product. But when you use the modified LiLH4, that's the LiAlH thrice at the 0 degree Celsius, so we get the only reduction of carbonyl group. And when you use the third butyl substituent at the 0 degree Celsius, that time we get the again the both reduction of the carbonyl as well as reduction of double bond. When you use the NaBH4 in the ethanol at 0 degree Celsius, also we get 100% yield of the product which has the reduction of the both carbonyl as well as double bond. But when the moment we add the CeCl3 as a salt in the reaction, in the methanol solvent, we get the exclusive formation of the only carbonyl reduction, keeping intact double bond in the product. So this is what some reagent combination. If you use the 9-BBN THF, in that case also we get the 99% of the reduction of the carbonyl compound selectively by keeping intact alpha beta unsaturated double bond. So please have a look at this table. And here are some examples with the some different reducing agents. So you can have a look at these some problems. So I will just keep this problem. So you can just refer this problem. So I don't think really need to discuss this one. So the first one is the first reaction with the NaBH4. So obviously it will reduce the only carbonyl group, keeping intact ester group or alkyl halide group. Then we had the BH3THF. In that case, it selectively reduced the acid, keeping intact double bond, also ester group. And when you add the BH3SME3 in this compound, the starting material, if you look at the starting, which has the ester and the acid, so it will reduce only selectively acid group. So these are the some reactions of the different reducing agent on the different starting. You should note these some examples. All right. So this is what I want to highlight from the reducing agent part. So does anyone have any doubt up to this one? All right. So we'll move to the. So I hope you have covered most of the reducing agent in this today's video. So I like to also take some of the problems. So based on the now it will be based on the week 10 content actually. So we have already covered week 9. So these problems based on the week 10 topics. So the first question is among the following, which is the strongest bond? So we have given the oxygen and the silicon bond, then the silicon and the chloride bond, silicon and the fluoride bond, and carbon and the carbon bond. So which bond is stronger come in this one? So in this one, the higher electronegativity difference. Uh, so the percentage of ionic character and the bond energy uh, is increases. So therefore, uh, silicon and chloride has the highest electronegativity difference, and this bond is the strongest bond. So if we look at the periodic table, so the size of the fluorine is shorter compared to the oxygen, which is compared to the carbon, and then compared to the fluoride. So silicon. fluorine bond is the stronger bond. The next question is, among the following molecule, which one is which has the higher planar geometry? So if you look at the all the structure, we need to draw all the structure. So that's the triethylamine. We have the first, there is a lone pair of the electron on the nitrogen. And if you look at the structure, so this will be CH2, and obviously there is a CH3. So that's the triethylamine. Then we have the nitrogen, which has the lone pair. Then we have the silicon, which has the three hydrogens, with the three hydrogens, and the silicon with the three hydrogens. Then we have the nitrogen with the lone pair of electron, one hydrogen, and the two isopropyl groups. And a third one, the fourth one is the nitrogen with the methyl group. So in all this case, if you look at the among which has the planar geometry, if you look at all the structure, so in the, I will label this better understanding. So if I just label this the A, B, C, and the D, so this methyl group doesn't create much steric load compared to all. So therefore, this has the um, less planar geometry, right? So this has the D has the less planar compared to the if you look at the structures, so which has the isopropyl group, and this is the hydrogen. But in this case, all are the ethyl groups. So therefore, I believe this A, then there should be a C, and there should be a B. So this should be the order of planarity, because of silicon, the bond is silicon is the bigger atom compared to the carbon, and therefore it should have the uh, more planar geometry. So if you look at here, and also there is one reason, this P to D bonding is also possible with the silicon. So if you look at this nitrogen, along with the bulkiness, so this silicon has the vacant d orbital, and this lone pair can possibly goes to this one. So it might induce the some sort of double bond character, and as a result, the silicon H3 uh, thrice nitrogen has the planar geometry, more planar geometry compared to all other. Then the third question is, uh, silicon are called inorganic polymer due to the absence of, uh, we have the four options in the main backbone chain. So whether it is nitrogen atom, hydrogen atom, silicon atom, or the carbon atom. So the silicon are called as an inorganic polymer due to the absence of, obviously the due to the absence of carbon atom in the main backbone chain. These carbon atoms, they are basics of the organic chemistry, but they are absent with the silicon based materials. So therefore, this silicon is called as the inorganic polymer. Next question is, which is the correct statement for the organosilicon compounds. So if you have the organosilicon compounds, so which statement is correct? So the first one is the silicon stabilize the positive charge on the beta carbon. Silicon stabilize positive charge on the alpha carbon. Silicon stabilize negative charge on the beta carbon, or the silicon stabilize positive charge on the gamma carbon. So which one is the correct statement here? So due to the beta silicon effect, silicon generally stabilize the positive charge on the beta carbon atom. So this is due to the beta silicon effect. So the option A is the correct option here. Silicon stabilize positive charge on the beta carbon atom. The next question is based on the reaction of this compound. So we have the one compound which has the primary alcohol, secondary alcohol, and the tertiary alcohol. And when it react with the TMS chloride in the one equivalent, so which will be the product? So obviously the alcohol which has the less steric crowding will be the get substituted. So when you add the one equivalent, so it will definitely substitute the primary alcohol. So these are some problems that I like to take from the week 10 topics from the week 10. So I hope I'm able to cover most of the content today. So we'll stop here for today, and I will wait for some time to if you have someone have any doubt that in the today's discussion. I will cover some more problems today. This another same problem that I should discuss today only because it's the same concept based on the earlier question. So here, in this question, so we have the starting material and on which we have added acetic acid and acetic anhydride one equivalent. So you can see here the compound which has the one, this is the primary OTMS group. Then there are other secondary OTMS group. So in this case, when you react with the acetic acid, this OTMS, so the deprotection reaction takes place. So the deprotection of this, the primary is more favored compared to the more faster also compared to the secondary cellular ethers, and therefore the deprotection of these primary cellular ethers are takes place, and followed by since we have added acetic anhydride again in the reaction mixture, so the deprotection of the primary TMS followed by the acetyl protection of these primary cellular ethers are takes place. So the option which option is correct here. So here you can see the option A is the correct option here. So in which the only primary TMS ether are depleted followed by the astral protection reaction takes place on that one. So the option A is the correct option here. The other options are, if you look at the other options, they have added here. So these are the wrong. So any doubt up to here? So we'll stop for today and see you on the next Tuesday. Right. So here, due to the steric crowd, uh, the order of the reactivity of the first one, the deprotection of the silyl ether, and the second step was the followed by the protection with the acetyl. Gives the product one is the major product in this case. So these are the some the problems for today's uh, session. So I will upload the same presentation slide in the drive as well. Right. So you can refer the video that I will upload on the YouTube and followed by the link of this slide also. I have already uploaded in the sheet, so I hope you are able to access that one. So any doubt in the today's session? So if you don't have any doubt, I will stop here for today and I will see on the next Tuesday.